All right, distribution curves. Distribution curves show the fraction of each species present as a function of pH. So we plot the change in pH versus the concentration of the acid and its conjugate base, or the base and its conjugate acid. So if I start out with acetic acid, as I add more and more hydroxide, right, I increase the pH, the concentration of the acetate goes down, and the concentration of its conjugate base goes up until I get to a point where the concentration of the conjugate base is equal to the concentration of the weak acid. So at this point, the pH is equal to the pKa. And at this point, you've got what you call the middle of the buffer range, right? Maximum buffer. So you're equally protected at this point against an increase in hydroxide or an increase in acid. So notice as the, how the line goes, right? There's no big change in pH as long as I'm in this zone, right? I could add some hydroxide or add some H plus and I shift back and forth. It's only once I get outside of this zone, once I've worn out either the acetate or the acetic acid, that the pH it really goes up, or if I'm going the other way, really goes down. Bicarbonate, right? It's a diprotic acid, so it's got two buffering zones. Hey, this is an important buffer in our blood, right? If we bubble carbon dioxide into water, it forms carbonic acid, so that's the acid that's in our blood. So we get a protection against spikes in pH. It's important that at all times humans maintain homeostasis. So the conjugate base of carbonic acid is bicarbonate or hydrogen carbonate. So the middle of that buffer sits at around just below 7, 6.83. So at that point, you've got the pH equal to the pKa, and you're equally protected against carbonic or hydroxide being added or H plus being added. Then we go past that, right? We burn up this buffer, and we're left with just hydrogen carbonate. At that point, as the hydrogen carbonate concentration goes down, its conjugate base carbonate goes up, and we get a new buffering system up in the basic range. All right, so the pH is equal to the pKa at a pH of 10.3. When we're making buffers, we want to pick a acid where its Ka is or its pKa is close to the pH that we want. So that's how you start this, right? You say to yourself, all right, so what does the ratio of the conjugate base have to be to the acid to buffer at a pH that I'm interested in, right? And you pick a pKa close to your pH. All right, the center of the buffering range is when the weak acid concentration is equal to the base concentration. pH is equal to the pKa. So choose your weak acid and the conjugate base. Set the ratio gives you a, you would pick a pKa that's close to the pH you want to buffer at. That's all. So how would you prepare a 1 liter carbonate buffer at a pH of 10? Well, the pH of 10.1 is going to be our pH that we want to get. So it's a question of what does the ratio have to be between the acid and its conjugate base? And which acid are you going to use? Are you going to use carbonic acid, which is going to be up in the acidic range, or are you going to use bicarbonate, which is down the basic range? So the pKa of bicarbonate is much closer to 10.10 than the pKa of carbonic acid. So I'm going to make a buffer using hydrogen carbonate and carbonate. So I plug my pH in, the pKa in, and I solve for what the ratio's got to be, right? So subtract 10.3 from both sides, take both sides to the base 10, and we get a ratio of 0.6 moles of carbonate to 1 mole of bicarbonate. So this is what this 0.6 tells you. It's the ratio I need of carbonate to bicarbonate to make my buffer.